All right. So day 4, we start with naive Bayes and we start with naive Bayes analysis. What actually the experiment says is very simple. It's not too clear as to which one should we be using. A program to implement the naive Bayes classifier considering all of a T-phase data set for training, compute the accuracy of the classifier considering a few test data sets. Okay, so of course we'll need to divide the actual data set into testing and training, which is just done in one code line. But what is this data set all about? So this data set, when loaded, looks like this. There are about 400 images. Each image is a grayscale photo of the person's face. 400 images are there. So it means what? It means your data set is a very small data set. Okay, just 400 images. Each image is a grayscale photo of a person's face. Grayscale photo. Okay, 40 people. The data set contains 40 different individuals. Each individual has 10 different images. Understanding what I'm saying? 400 images are here. How did you get 400? 40 different faces, 10 images. So this can be this. Usually image processing problems are not solved using these kind of classical machine learning problems. Image processing is solved in high dense data sets, high density data sets. That is, you use deep learning. Here in this case, naive Bayes is used, or naive Bayes is proposed to be used, because this is that kind of an algorithm actually. What is naive Bayes analysis anyways? So naive Bayes analysis, let's go and get that. Understanding naive Bayes is important. Otherwise, you will feel somewhat like you're just trying to do a formality sort of thing. It won't feel good. Let me just give you a sense of what naive Bayes is doing. Naive Bayes is one of the very versatile machine learning algorithm. Naive Bayes is used for your your email classification also. See, it is used for email classification, which is text. Now we are doing it for image classification, which is pixels. Okay. So somewhere text is converted to numbers and pixels also have to be converted to numbers. But what is naive Bayes actually doing? Naive Bayes builds up a probabilistic model which says the probability of A given B. Probability of A given B is P of A into B bar A divided by P of B. It means the key insight is the probability of something that depends on B. The key insight here is the probability that something that depends on B. Probability of something that depends on B very much also depends on the base probability of A. Okay. So if you are setting up a problem, basically, I'll tell you what, this equation you might feel a little confused. I'll simplify this equation even. A and B are events. Okay, let's say A is an event, means learning ML lab after attending the event. Mhm. Mastering string ML lab. Second event is attending ML FTP. This means what? Probability that somebody will master ML lab after attending ML FTP is equal to, see, now you understand the, so that is PA. Yeah. Attending ML FTP, mastering ML lab. What is PA? PA is an independent probability of all the people who has mastered ML lab, regardless of whether they attended FTP. Into P bar A. All those people who attended ML FTP to master ML lab. So this is a reverse event. How many of them attended ML FTP, which is attend ML FTP after mastering, divided by P of B, which is the probability of attending ML FTP, the probability of mastering ML lab. We can actually get this data if we can take the entire data set of all the colleges and all the people assigned the ML lab, right? Like you, all of you are here, and so many people, 156 people were there in the beginning. And there'll be more actually when you talk about VTU, there are so many branches. Everybody has ML lab. So if you take in all of that, you have to calculate what is the probability that somebody will master the ML lab because they attended the ML FTP. That is equal to probability of mastering the ML lab itself. Whether you have, so you ask everybody, how good is your um, uh, person? Okay, these are dots. This is did they attend ML lab? So person and have they mastered ML lab? Okay, so think like that. Did they attend? Have they mastered? People. So you will see that some people will, if they attended, and they would say not mastered. Some people will say attended, and they'll say yes, mastered. Okay. So some people say not attended, still maybe mastered on their own, right? They would. So there are different combinations out of which you will get PA, which is mastering MLAB regardless of whether they attended it or not. So total here. This is probability again. So probability is again something by something, correct? So what is this? Probability of A, that is mastering. So if there are 500 entries over here, of which the green is say 110. So 110 by 500 will go here. Certainly will calculate for this probability that so that data is against a survey data. You have to do a survey for this. So the probability of already who had mastered, who attended the MLFTP probability, which is very less, as you can see, right? This won't become more. This is very, very, very rare. Okay, and then P of B is attending MLFTP. The probability that somebody attended that is here. So this usually will be higher. People attended and people who have mastered and this one. So when you compute this, you'll get one number that will give you this conditional probability. So that is your conditional probability solved using naive Bayes. What is happening here is this is the extra effort. You not only consider here you're trying to calculate the probability of A after B has occurred, and the naive Bayes equation says if you want to see the effect of B on event B's effect on A, that's what attending MLFTP's effect on you mastering MLab. If you want to see the effect of an event B on A, you should also consider the effect of A on B. Two events, both interchangeably, you have to consider. So the Bayes probability, it will have to. So that is what naive your Thomas Bayes proved, and why it is called naive. It's called naive because naivety is innocence. So innocence means this conditional probability, whatever is there right here. How do I put it? Naive is naive because it sort of assumes that every event independently affects outcome. Interdependency is not checked. Like for example, there is a, let's say there is a data set. Bird has wings, can fly. You're asking this, okay? If it is a bird, one, it has wings, can fly. If it is a bird, it has wings, can fly. If it is not a bird, doesn't have wings. So wherever there is bird, and if it has wings, it can fly. This is a redundant. You see, this one asking whether there's a bird and then also asking if it can fly is a redundant feature. Wherever there will be one here, it will be one. If it is zero, it will be zero. It will be mirrored. But naive Bayes, what it will do when you give a data set like this, it won't understand. It will consider this also and this also because that's how it is. So that is why it is called naive Bayes. Otherwise, it's not the name of the person. It is the sentiment attached to it. It's naive Bayes. So that's what this whole thing is about. So that is the fundamental. So now what you do, you have 400 images, out of which 10 each. So you have 40 unique faces. Now this model, whatever model we take, we will take, let's say 40 some person A. This person's one image, okay? A2. This is the person. This is the image. One is the image of the first image of person A. 2 is the first image of the second image of the person A. Am I audible? Am I following? I sometimes maybe. Thank you so much, sir. Thank you so much. Ajira Begum ji, thank you for your wishes, really. So making sense, right? So all this thing. So if you have this and you have A3 and you have A4, you have A5, you have A6, 8, 10. 10 images are there. And you will tell this is how you train, right? You say these are my 10 images and it belongs to the person A. The machine has to understand, the machine has to learn that person A has a certain feature. So in the first image, it will learn something. In the first image, you see the images are also very different. There's Olivetti face. This you can see. Let me snip it off. So instead of me giving some hazy idea, I'm going to make this a person A. This is A1. This is A2. This is A3. This is A4. This is A5. This is A6. Blah, 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 blah. Till A10. Okay. This person only. Think about only this person. This is another person. So in this data set, 10 images are there. And like that, 40 people are there. That's what makes it 400p, right? Now we have used both Gaussian NB and multinomial NB. Usually Gaussian NB is preferred. Multinomial we just tried. You can use it or you can drop it. But multinomial gave us a better accuracy. That is the here. See 73.33% we got it. So on the code and all I'll explain. Code we'll send you an entire manual of explanation of each line, because a lot of things over here are image processing. First, let's understand what we are doing. I guess you're already sort of familiar now as to what is happening. What was I trying to show here? Is the 400 target loaded directly from sklearn.datasets import fetch Olivetti faces. Okay, just in case if people have joined late, so to understand that we have loaded this data, then I've snipped it off. I've taken it here. There are different images. It's a small data set. That's why a naive Bayes is used. If this was like a drone image trying to do something critical in the border, then the naive Bayes and all will not work. But what is happening is in naive Bayes, okay, what I was trying to show was I've used two codes. One is here, see, import Gaussian naive Bayes. NB is equal to Gaussian naive Bayes. NB.fit X train, Y train. Y predict is equal to NB.predict using the X test. Okay. Then using both the Y test and Y predicted and rounding it off to 2 points and multiplying it by 100 to get percentage. You will get that answer and finally you will get 73%. Okay, this is which accuracy Gaussian NB. Then I think we conducted a multinomial NB also. Okay. Which gave us 85.83%. So if you want to see what multinomial NB does, I have something. There are two. If you want to do it, then you can do it. Otherwise, it's fine. We just wanted to see which one can give us better. So multinomial NB is like this. There you saw, right? P of A, P of B, you saw that, right? There, multinomial NB, in multinomial NB, what happens is you can test many cases. Earlier we saw, let me take this example. Basically, I don't have to explain too much to you. This is a animal classifier problem where there are all these data sets and we have this to be classified. If something can swim and doesn't have wings and is green in color and doesn't have dangerous teeth, what kind of animal it is? So we built that one to get you that. So, but in this case, you should understand the difference between Gaussian NB and see here, what is being calculated is probability that something is a fish, provided it can swim, is green and has dangerous teeth, is equal to probability of a fish being able to swim into probability of a fish being green into probability of a fish having dangerous teeth into probability of being a fish divided by probability of all the things in the data set which can swim, be green and has dangerous teeth. Like this, okay? So same multinomial. Now Gaussian NB and multinomial NB are approaches which are different. Gaussian NB, what it takes is because your picture is a set of pixels and each one of this, if you zoom in again into it, how do you think the computer looks at it? The computer only looks at the pixel density. Okay, the pixel variations, the variations in the pixel, the brightness, the darkness. So everywhere it is trying to fit some kind of a Gaussian distribution here. Just by getting the Gaussian distribution around one section of the image, they'll know what is the gradient here. So this picture gradient is like this. The same person on the second, the gradients are like this. It understands the gradient here. Why it is understanding the gradient? Because see, from here to here, as the image moves from here to here, something is getting darker, darker, darker. And it knows the angle also, how it is getting darker here. So who will model this change? It has to be modeled with a ready-made function, right? We can't recreate any function. Ready-made function has to be tailored. So Gaussian PDF, whatever is there, it helps us to identify. Basically, what we'll check is, when I say Gaussian, we'll say just say how close is this distribution to our ready-made Gaussian curve. That is Gaussian NB, right? So if this in the first phase and this in the second phase and this in the third phase is all equal to A, means the probability of a person being A divided his first image Gaussian was like this, or some G1. Second image Gaussian to be of value G2. Third image Gaussian to be value G3. So like this it will compute, and finally it understand mathematically that the pixel variations of the particular image, there is a particular pattern of this person's pixel variation. Person, this first person and the second person, they are completely different people. We also know our eyes are tuned to identify features. Machine will only do it the hard way. To help the machine, we have to feature engineer. And the features that we are giving it are the Gaussian distribution. The pixel and ask the Gaussian knife base to do the analysis, and Gaussian knife base internally will know what it has to take from this. The end goal, End goal is next time we show this face, the machine should say that, hey, this person is A. So is naive Bayes, Gaussian naive Bayes able to learn it better, or the multinomial naive Bayes is able to learn it better? So multinomial is showing us better results, because when it comes to multinomial, it computes the probability that A is A. Multinomial's way of thinking. GNB's way of thinking is it will take all the pictures and it will say, divide this and say, in general, my first left half should follow a certain kind of Gaussian distribution. My second half should follow another kind of. So in general, it will study everything. It will study this part of this. Then it will study this part. 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 Then it will combine everything and generalize one PDF. That is what? Probability density function. Density of what? The pixels. Right. So there will be in fact, you can go lower and lower. Nobody is stopping you. Just telling you, you can go lowest and get a, you can completely change this image into small pixelated section where the Gaussians are calculated for all. Okay. But that then what happens? Like next you give an image, it will check this part of the image and it'll say how close is this image to A or B or C or D, because this is also there, no? When you give this person's picture, it will check for all and it will say whose distribution it is closest to, and then it will take a prediction. Okay. So now what multinomial naive Bayes does is it will say A is A because when the person was staring at me, the distribution was like this. When the person had slightly tilted, the distribution was like this. So it is like that, where I said probability of a fish, provided it can swim, be green and have teeth. Probability of being A, provided that his straight looking face has this distribution, his right looking, the second image has that, because we know that not many are repeated here. Okay. So for each of the sample, if there are 10 samples, we know that there are 10 uniques, and we know for each unique there are 40 uniques, and for each of the 40 we have 10 faces. We know this already. So it is going to take the case of all the 10 examples, that sample, and it will build a conditional probabilistic model for it. That's all. So we come back. That's all there is to this. See how simple the code is. It's hardly anything. 400 images. Each image is a grayscale photo of a person's face. 40 people. The data set contains 40 different individuals, and each individual has 10 different images. Okay, just a second. So we are going to load that data set. Okay, 40 data set contains 40 different individuals and 10 different images. All that is fine. Shape is okay. This is something. Images are reshaped 64 by 64 into one-dimensional features of the size 4096, resulting in 4096 feature flattened vector. Okay, yeah. So that is a different, as I told you, image processing. This one, so it will just flatten it because using it as 64 by 64, then it will be a huge matrix to handle. Without losing much information, it will just get flattened as a vector. So this flattening of the vector, how do I say, is how it's like yeah, same way like how you reduce the PCA, right? Using a PCA, how you reduce the dimension. The 64 by 64 dimensional problem is all projected onto one vector. That is a flattened vector with so many features in it. Okay, so next what we do is train a naive-Bayes classifier on it. So we load this data.keys data, and we just target and description of yeah. There's a description. Where's the description? The size of the images, so and so format. Okay, so print this. So you got this data shape 400 images with 4096 pictures of it. Create shape 400. There are 40 unique persons in the data set. Size of each image is 64 cross 64. Not audible? Did I go completely low on the voice? So this is the first, we're just trying to print the faces here, okay? So print faces, images, target, and this one. So images, a collection, this images, okay? This one, already have that. It's a NumPy collection. Then all these targets are the labels associated with it. The top n are the number of images to get displayed. Okay, so top n is equal to minimum of top n length images. Basically, we want to make sure that this minimum of top n and length of images is make sure that the number of the images that displays doesn't cross the already available. So ensure the number of images does not cross available data. So that's the thing. Then we calculate the grid size. Okay. So how do we get that grid size? Grid size, set up the figure size based on the number of images. So you have this image, right? So you want this image because we are trying to print faces using all the images target and top. And so we want to print faces, data.images, data.target, and 400 numbers. So all together has to be printed, correct? So that's why we are trying to calculate the grid size using this. Why this is so? Why this calculation is so? It's sort of a little. It will require. So this one I will send it to you as a video itself, the explanation of the code. Here we'll fix the axis, the figure and the axis. plt.subplots grid size, and figure 15 by 15. So each one is a 15 by 15 figure. Subplots are just how much to the left, how much to the right, how much to the bottom, top, and all these horizontal and vertical spaces that are there. Okay, then for I and AX in enumerate access dot travel. This, as I told you again, a feature of That the ravels are the ones which are already where you already converted your image to a single one-dimensional file. So when you make access.ravel, it is the function which is flattening that image into one dimension, because that way we'll be able to loop through those images. Otherwise, it is very difficult. We'll have to have um, uh, two or three loops. So if you make it into one dimensional using this access.ravel, then you are able to now just do this. I in AX in enumerate. So you are enumerating all this one dimensional. And from that you have I and AX. Okay, I is the index and AX is the your current subplot. Okay, this is all subplots, right? So you take that, you take the subplot, and you display each image next to each other. Basically, this whole code is just print faces, just printing the face, all the faces together. See, print faces, I'm calling print faces here. Print faces, I'm sending the entire data set, then the target, and how many of them are there. All this information I'm sending, we need it. Using that information, this is where the printing happens. Okay, so each one has a value. What is this? AX stat, I'm show images, I cap CMAP is equal to bone. What happens here? Access AX dot access off. So you turn off the access because we don't need it. AX dot text 2 comma 12 string target I. So whatever text is put on here, right? Inside this, the text that you saw, what it should be. One is red color. The text at 2 comma 55 F face I. Okay, that is blue color. So all these are there. Where are these? We are getting this from this target. We got this target from data.target. Target has that information. Basically, we are trying to summarize the entire image here and putting this image and making sure that these target attributes are also put in the right place. So start from 2 and with 55 as this one. So this blues are down and all the reds are on the top with the axis at 2 comma 12. That much it has done now. Only printing of the face. To the next. Displaying the unique face. Let's extract all this. Where is that? One second. Print faces. Okay. So displaying the unique faces now is one second. PLT figure size. So you have to set up the number of sizes that you want for that. Earlier it was 15 by 15. Now you're setting up this one at 24 by 10. Set the figure size. Columns and rows 10 by 4. Define the grid dimensions 10 by 4. Right? You know there are 40 different people. Loop through the grid positions and plot each image. So loop through the grid positions and plot each image is I in range 1 columns into rows plus 1, which from here you will loop through, and then image index is equal to 10 into I minus 1. Calculate the image index. Whatever I value you got, last one of it is put into image index. You want that unique image, person 1. Unique image, this image, 10 minus 1. A0, A9. This is the image, right, which got in as unique here. Yeah, see, ninth face. So we can also see for this guy also, we should be expecting this face. See if it is true. See, that is what this is doing. Basically, we're just taking which image we want, the index of the image that we want, and again doing the print of it. If image index is less than the pix.shape, check for the valid image index, so of course, because you don't want to cross that image index also, right? So it has to check it. So once you get the image index, basically, see, this is how it works. You come here, you hop on, find the ninth face, take it separately. Then go to the next one, hop on, find the ninth face, take it separately. Once you take this separately, take this one and okay, take this. So all the things here, all the things which are here are getting selected. This got selected, this got selected, this one, this one, this one, this one. See, all of them. Basically, this is just a logic. Okay, you can, if you want, you train, if you want to put this, say you want to do a Viva on for your students, you should say, okay, you observe that all the 10th people have been selected. Why don't you, select only the second image as a unique image for all the people? So then they should know that, okay, they'll have to go and check this one out. They'll have to go and do something with this. This is 10i minus 1. Here they'll have to do some changes in the code so that they can only see the second one. Once they write it, then you can also check that, hey, okay, the fourth one or the third one here, 0, 1, 2, 3, the third one is a different image. So only the third images are getting selected as unique. That's all. Okay, so that's all. This code is one, you print all the faces at once. Then you print the unique faces. Unique faces code is here. And as I told you, line by line, each code, what it is doing, we'll send the explanation. That is okay for the manual, because if I explain line by line everything, no, you will not, it won't feel like this one. Not be able to connect it. Lot of computations are here. You will not be able to connect. So that's why we can send it to you as a separate document. With that document, you'll have to think. Again, that is not self-explanatory. That document, you have to sit with the code, use the document, think through, then you will automatically understand. But generally, you are understanding how these things are working with the video, which is always going to be there with you. You can, follow it up and watch this video again so that you can, whenever you later, if you forget also, it can come back and get the point, get that insight again. So that's it. All these things you can see easily. There are 40 different persons in the data set that is printed here. Font size for each 24. How much is the this font size? All that is fine. Now from sklearn.model selection, this is a package from which we are going to import train test split as usual. X is equal to data.data, y is equal to data.target. What is the data? Data is here. Data is equal to fetch Olivetti faces. Olivetti faces we got because we imported it from sklearn.datasets. This data is here. This data already contains, data contains the keys. Data contains data itself and what target you have. And then you, of course, do this X train, X test, Y train, Y test. You don't have to by heart this. This is something which has to be remembered. This is something left to you. You can just write XT, XTT, YT, YTT. Okay. So T is single T for us is train, T is for test. So we write XT, XTT, YT, YTT. So easily you can just get it. Here, of course, for the sake of for documentation, we have made it like this. The train test split XY test size is equal to 0.3, random check it to 46. You can change this, not a problem. Size is 0.3, so it is 70% and 30%, 70% to train, 30% to test, which is usually the case with your image processing problems. Okay, then you got this. You got this print xtrain. Okay, print xtrain. The shape of the training sample, the shape of the testing sample. This is 409896 features are there. There's nothing you can do. So there are 280 images with 4096 features for each. And this is flattened out feature. Otherwise, it was a 64 into 64 bit pixel, but that got flattened out into one-dimensional 4096 features, which we don't know what it is. It is just mathematically computed to be very different. Just like how we take those principal components like that. Okay. Moving, when we take this, decide to take a Gaussian NB approach. Sklearn.naivebase import Gaussian NB. Sklearn.metrics import confusion matrix and accuracy score. So I don't know whether you know confusion matrix or not, but let me see if I have. Basically, to evaluate a model, you have two metrics. One is accuracy score, another one is confusion matrix. Accuracy score is a general accuracy score of the model, but confusion matrix tells you if there is a pattern of error. Like the pattern of error means what? Pattern of error means you see these faces, you tell me which faces are similar, most likely to get confused. Most likely, see, they are all unique faces. Most likely, which faces you will get confused? I'm guessing this face and this face. There could be some other faces also, but it happens. We'll see now when the results come in, which means that many times when we have shown this 10 samples of this person, it would have recognized it as this person. So if you, instead of 1, it will say 9. Although all the features were of 1, but it misclassified it as 9. And next time 9 get misclassified as 1. So confusion matrix tells you that. Okay. So it's mostly like the actual yes and predicted yes. Actual no and predicted no. So if the actual yes, actually if it is yes, but it got predicted as no, how many times? Actually it was no, but it got predicted as yet, how many times? So like that, the misclassification, those, how the pattern of misclassification, generally if a particular class is being misclassified as a class of, it means like, let's say, always class A gets confused and gets misclassified as class B. But all other classes, class C, class D, class E, they never get misclassified as class B. So when you have a matrix which tells you this exactly, then it is better for you, right? In this confusion matrix, what we can find out is, see, was there a class A, class B, class C, class E? And whenever we were trying to classify, class A is usually getting confused with class B, but class C, class D, and class A are all okay. It never gets misclassified. But there is something with this class A and class B which are very, very similar. So we need to find more features to distinctly, what do you call? Distinctly code it. So what about class A is you have to ask more questions about these two so that we can find some distinction between that. So that the machine also can find the distinction. That is what confusion matrix will do for you. Okay. So accuracy you already know. How many Y predicted by Y test. That's all there is to this. So we got this Gaussian NB. We are using that Gaussian NB model, and I see confusion matrix is here. Naivebase accuracy is here. Yeah, NB is equal to Gaussian NB, NB dot fit X train, Y train, predict the test set results. Y predict is equal to NB dot predict X test. Makes sense? NB accuracy, again a new term. All this on the left are our creations. On the right are syntax. So round accuracy score, Y test, Y predicted. Again, you do this into 100 and round off to 2, because otherwise you would get 0.73 as the answer here. Don't do this. We just want to write it will 0.7, some huge number you will get. So we are just rounding off to 2 and make it into a percentage. That's what this is doing. Then you have CM0 confusion matrix, Y test, Y print confusion matrix. You got the confusion matrix. Then you got the naive Bayes accuracy. Similarly, we'll do for multinomial NB. There we have confusion matrix, accuracy score, and classification report, which probably we have not used the classification report skill. Oh, later. Oh, that is a misclassified image. Calculate the number of misclassified image. Got it. That report is important. Yes. Skill and matrix, import confusion matrix, accuracy score, and classification report. NB is equal to multinomial NB. NB dot fit is equal to X train, Y train. No surprises here. Y pred, again, you need that Y prediction should be equal to NB dot predict X test. This is the result. And when you compare this Y predicted and what you had already for Y test, that's your accuracy. The same thing. NB is equal to multinomial NB. This is where the model is built. So if you're wondering where is that, where did we take that image? This is where we printed the faces. This is where we printed the unique faces. And then we came down here. This is where we brought in the train test split. So we split the entire data into X and Y. And we are, for us now, X train and Y train is ready. X train and X tests are ready, means Y train and Y test is also ready. Okay, we just printed this. So otherwise everything is ready here, ready for us to consume. Once we know that is ready for us to consume, you import the Gaussian NB package or the Gaussian NB algorithm. Then the Gaussian NB is invoked here with our object name, which we call NB in our code. Then we say NB dot fit what? The X train and Y train, which is here. We split it. Where did we get the X train and Y train from? From here. What are X and Y? The real data's target. Okay, that's how this thing came till here now. After that, we used Gaussian NB, did all this. It's very, straightforward. Then we are using multinomial NB. Only thing now is we have something new, which is classification report. So take multinomial NB, do the same stuff, and then you see that here the accuracy is high. Somebody, if you want to know why the accuracy is high, I already explained it to you, because multinomial takes the dependencies like this. Not just generalized one picture, just like how Gaussian will do. Multinomial will check if this also has to be done, if the eyes also should be like this, if his eyes is like this and mouth is like this and head is like this and this is like that, then this person is this person. No? You understand what the image is doing? That P, A bar, B, comma, C, comma, D, comma, E. That multinomial probability. So I hope you're getting a little bit of understanding of multinomial. Otherwise, I'll eventually send you more videos on multinomial classifications. Now calculate the number of misclassified images. Misclassified index number is equal to NP, where your Y predicted is not equal to Y test, the 0th value of it, because you want the count of it, I guess. Yes. So misclassified index count, how many of them have been misclassified? The condition is wherever the Y prediction was not equal to the Y test value. The number of misclassified events are length of the misclassified indexes, because that's what you got here. Which index number misclassified is put here. Now, how many index numbers are there? The length is the total number of misclassified values. So I think total number of misclassified images are 17, which you got from here. So print number of misclassified images as misclassified. Then total images in a test set. Oh, total over 120, because we saw that, right? What 280 was training, 120 was testing. which is here. Where is that? 280 was training, 120 was testing. So that is there. Accuracy is 85.83, fine. But this is a misclassification report here. And misclassified to show is equal to minimum of the number of misclassified, minimum of these two. If number of misclassified are number and there is 5, this becomes more, then at least show 5. So show up to 5 misclassified images. So minimum of these two numbers. But in our case, misclassified is 17. So it's 17, 5 is picked up. So misclassified to show is 5 now. Figure size 10 by 5. We need to plot this 10 by 5. Is it true? It's not 10 by 5. Okay, this I'll just get back to you on this. Okay? For I in range n misclassified to show, this is n. So I in range 5 now, because number of misclassified is 17. So 17, 5, you get 5. For I in range 5, index is equal to misclassified index of I. Whatever is the first 5 misclassified index, that index is here. Then plt.subplot 1, comma, n misclassified to show, comma, I plus 1. Okay, this 1, first it will do the subplot, then it will increase and leave it. Okay. Then plt dot show x test index dot reshape into 64 C map is gray. So again it will reshape back to 64 by 64 because it was one-dimensional feature. It had been converted to one-dimensional feature, right? So that is why the x test value x test, because it were test images. So this got tested, and what now here by plt.title is white test, the index of it, and predicted ypred, the index of it. The same index is getting followed. I hope you are seeing this. Once you got this, no, this index, everything is same. So I hope this one is clear, because we are getting that index anyway from which value this is. This is the first value of that image that got in. This was actually 34, but the system predicted as 20. This is actually 12, but it predicted as 7. So let's go and check, just for interesting, just to make it interesting. What was this? Person is 34, but got confused with as 20. Okay, so where is that 34? 34. Person is this is from 0, right? So this is 35 written here, but it is actually 34 because the number is named from 0 probably. True is 34, predicted is 20. True should be 34, but what got predicted was this. 1 minus, because it is starting from 0. Person 0 isn't there, that's why. This person's face and this person's face got confused. True 12, predicted 17. Truth is 13, means 13. Okay, 12 and predicted as 7, that is 8. Achha. This person got predicted as this. Okay. Okay. Anyways, I hope you're able to follow. I'm putting all these things. Next, we use something called label binarizer. Binarizing the test labels like this. like this. Now class 0, what is the AUC curve? It's as simple as that. You take white test bin label binarizer, take the white test and the classes.np uniquely, all the unique values of white test. Of course, those are the classes. That's why you get the class here. And the white test value is given because you want to, just give it as a yes or no kind of binarizing it. Get the predicted probabilities for each class. Okay, white predicted probabilities with nb.predict probability x test. And print the AUC because you need to get that AUC. We need this for I in range white test bin dot shape. 1 second, just a second. 1 second. Okay. So where were we? 39 is missing here, right? This particular piece of code, I have some, this one, I'll explain everything here. White test bin and I white thread bin probability. You can remove this if you want, but I'll send you the explanation for this. I'll send you this because I'm not convinced, because I'm a little here. One value is missing, which did not see through earlier. I want to make sure why it is missing, why this is getting calculated. I want to put some graphs also for this. So I'll update you on this. This AUC is area under the curve. This area under the curve which actually tell you how good a fit it is. So when you have AOC as 1 here, this is the metrics again, like how you have accuracy, how you have confusion metrics, you have AOC curve also. Okay. What AOC curve will do is it will give you some number. But what it does is if it is 1, then it means that class 1 is completely classified properly. So there is no confusion. If this AOC class 20 is 0.52, it means that 50% of the time they will know that this person is this person. The rest 50% of time it will just be something else. That is what it is saying. Okay, but of course from my end I wanted a more deeper explanation, but yeah. So I'll get it done when I'll send you the code explanation as a PDF, right? So there I'll send you all this. Just like how I sent it for LWR, each one what it is doing and everything. So I'll explain everything in terms of diagrams and I'll send it so that it is much easier for you to follow it. Okay, I think this much is the one for what is one. That is what is meant by AUC, area under the curve. So Swapnaji, that is area under the curve. Okay, so area under the curve means there is a probability function where this is the total probability of this total probability. How many times? That's why you have this white predicted probability and white test bin. So predicted probability, you're calculating it. How many times did a particular class get predicted properly? That is what this is. So that is why area under the curve they call it, because this curve is a PDF. Okay. And everything under this curve is the total probability. So when the total probability is this much, one of the samples below we just saw, the samples below is a 0.16. So you will just get a very less space where it got classified. So now this is 0.16. Class 17's C curve looks like this. The total area under the curve is this much only. Baki it is not able to classify. That's what it means. But then I'll send you the real. This is just understanding. We understand it, but understanding with the code is a little different. So as I told you, this particular this one, and I was just thinking, I was just wondering where is that? I don't know whether I missed it or not. Where is that class 39? Why is it not there? Why is it only from 0 to, it should be 40, right? What happened to that is what I'm wondering. I didn't observe this when we did this. Now when I'm doing this, and suddenly it occurred to me that where is it? It was supposed to be properly structured. Anyway, so I'll get that answer. I'm not saying we are all perfect. But don't worry, so I'll send that. But hopefully this all of it is clear to you. Not much, as you see. It's simple. Simple. What do you say? We close this, go for a break. We come back in 15 minutes and take KNN. Great. Thank you. So I'll just stop recording so that this records, this section of the experiment is recorded separately.